Okay, everyone. Okay. Okay, let's get started. So, starting from this week, we are going to cover two different topics. One is spatial data model, the other is temporal model. So we'll spend 2 weeks on spatial models, this and next week, and then 1 week on temporal models. So this week is more like a introductory to the data model and the type of queries we can run. And next week is more on like indexes and how we execute queries. So it's about spatial data. Okay, so today's lecture is going to be a bit short because there will be like a project demo right after this, and usually it will take a long time, so we want to start that a bit early. So for this demo, we require all members to be there to get marked for the project. You have to be there. You have to attend the demo to get marked for the project. If you can't, you need to let us know, and you need to have valid reasons. So we have a lot of groups per lab, and we don't have much time. Like at most probably like 2 hours per lab. So we try to start demo today from like 7 o'clock or a bit late, like before, at least before like 7:30. So each group probably have like about 10 minutes time. So the main purpose is we're not going to ask you to run every single queries you've designed and implemented. We don't have that much time. So the main purpose is for the markers to basically get some idea of your design and implementation. So while they're reading your report and check your script, they can easily grasp what you're trying to do. And also, so you will demo a few, and you also show your design. And another important thing is to work out member contribution. So we want to ensure that each member contribute roughly like equally to the project, and if you have issues, you should raise it during the demo and let the markers know. So if the contribution is not like evenly distributed, the marker can decide like a portion, and then the members might get different marks. So majority of the marking will be done like afterwards because there's no time to check every single query. There's so many queries. So you don't need really to argue a lot about like different results, things like that. So what we expect is like each member should be able to independently answer some questions, and then regarding the schema design, query design, and execution. So it's not like you attend and you don't be a passive member. So each member should be pretty active with the respect to the part that he or she is responsible for, like independently run some query. So to make sure the demo can run smoothly, we expect you to set up the environment, like your systems, and especially like load the data before it's your turn, and your tutor will decide. We'll ask who is ready, and then we'll try to demo. We'll try to sit beside the group that's already like ready. And yeah, try to avoid arguing with markers like result discrepancy. We know that because the data is not very clean, and like the data format, there are a few of them. So depending on how you process it, you might get slightly different results that's acceptable. And also you may interpret the query in a slightly different way. And again, that could be, most of this would be acceptable. So if you find your result is slightly different to what the tutor, in the tutor's demo sheet, that's fine. Okay, and most of you have already signed up to a group, and now the group has a name, which is the lab's name. So it doesn't matter which lab you go normally, but you should go to the lab which your group name indicate. because that's where so the tutor also has like a list of the groups in their lab, and then they expect you to show up there. Okay. Yeah. Now that's about the demo. So, for the Wednesday ones, we have like 2 consecutive ones, and we try to book the other and like book 6 to 7 in each lab. So for like overflow thing, and your tutor will try to coordinate with you like when should you do the demo for Wednesday, for student doing lab on Wednesday, doing demo on like Wednesdays. Okay, so we move on to the lecture content. It's about spatial data. And first, a little bit on the motivation. So basically, it's because when we say spatial data, it's like the data that has physical shape and physical location. And we really want to measure it, to measure those physical things, not just like as a number. So because it matters for business purpose. So it's like, so the items might be located at a particular place, like the geospatial one, like we want to find store near the customers. So the customer has current location, the store also has a location, and we want to be able to calculate the distance on the fly, and then to help the customer to find like, the nearest stores. And yeah, certain items like have extent or shape, and like if we have the questions of we have like big boxes and there are lots of parts, and the classical question is how do you fit those boxes, like parts in the boxes. So all this like physical things like actually matters. Yeah, so we're focusing more on this geospatial data here, even though the same can be applied to those shapes things, but we're basically focusing more on, when we say spatial data, is more about this geospatial data. Yeah, there are a large amount of them, like business and home have address, Google Map or Google Earth, all of this. Yeah, there are lots of applications of the spatial data, and you can recognize some of this you probably use like basically every day. Okay, so why we want some special things to handle it? It's because, yeah, well, we can use any regular storage systems to store those and then run query on it. But that would mean we have to write a lot of customer code and basically write a lot of, like different person needs to write this, to re-implement the similar kind of things again. So that's not very efficient, because we kind of, there's a requirement that, okay, there's a repeated, like a common usage for this kind of thing. So we want to have a system or have a component for certain systems to handle this. So it's possible to store this data in like a regular database. Like if we have a spatial data representing census block, which is some kind of shape, here to make things easier, we just assume it's like a square shape or rectangle shape. So we can have like a table called census blocks, and the table may have a few attributes that's just of regular type. So the census block has name, has area, which is like a floating number, and has population again, which is like an integer, and then the boundary is like a physical shape. So the boundary like bounded by different lines. So we can create like a user-defined shape called the polyline, right? And then we just remember each corner of those lines, and then they become, and we connect them, they become like a shape. So we have this polyline starting from like 0, 0, 0, 1, 1, 1, and 1, 0. So that's the coordinate. So this is like if we have the object concept, we have like user-defined object, so we can do something like this. So in pure relational format, it's like assuming we can't really define any type. We have to rely on all this predefined simple type. Then we need to basically have quite a few tables. And then we have to join them together. So we have like our main table, which is census block with name, area, population. And then for boundary, because it's like complex type, we can't really put it here without the user-defined type. So we need a reference. So we only put an ID here and referencing something in another table called polygon table. And in this polygon table, we used edges to define the shape. And then for this particular ID, it has a few edges. So again, because edges is also like a complex type, so we put it in yet another table. It's like this edge has each edge has like two endpoints, two, and then for each edge we have two rows here. And again, endpoint, again, like a point has like a coordinate. Again, it's not a simple type, so we might reuse them. So we save the point in yet another table. So we need like 4 tables, like in the pure like relational form. And again, then to be able to get this boundary shape, we need to join all of them together. So that's just for storing. And then if you want to do some kind of processing and then to involving multiple shapes, then without like a specialized system, you have to write a lot of customized code for that. So that's why it's much more efficient if we have a system that can handle all this common type and common processing. And that's what we call spatial database management system. So it's basically a software module that usually can work with underlying DBMS, because most of the time we are dealing with spatial and non-spatial data. So we don't design a system just for spatial data. So it's more like a sub-module belonging to a regular storage systems. And basically then it supports spatial data type, like abstract data type, and common type of queries. And usually they use indexings to facilitate like a query to make it more efficient. And usually they also implement efficient algorithms for common type of processing for the spatial data. And sometimes like domain-specific rules for query optimization, because we can't rely on pure relational algebra now. We have to use some spatial knowledge in it. So many relational database management systems and also some of the NoSQL storage systems have support for spatial data now, because they gradually realize it's a very important data type. And many like applications will need it. So like Oracle, SQL Server, MongoDB, both MongoDB and Neo4j actually support spatial data. Not in their first few versions, but it's more like a later addition, indicating like they're aware of the growing importance of such queries, such data models. So usually they consist of like models, but they most likely it's using the underlying query language, and sometimes with special extensions. And this has query processing, like, the different ways of organizing the files and indices, and different ways to optimize queries. Okay, let's see what's the typical way of modeling spatial data. There are 2 typical types, but again, we're only focusing on one of them. And then we'll see what's the coordinate system, and what's the typical operations we want to do with the spatial data. Okay, so the two common models, one is called field-based or space-based. The other is called object-based. So we're focusing more on this one, but we'll briefly mention this one. So this is also, this basically try to model the properties of the underlying space. So it's like there's some space, and then within the space there are certain properties, like if the space represents like a mountain, and then the elevation of the mountain becomes like the properties. And then at a different point, the elevation will have different values. So it's very good for expressing like values that varying continuously over space. So it's like the space is not just representing like a single property. And so within the space, like there are lots of, within like a space, there are lots of, the property basically changes. And it's not changed in a discrete way, it's like in a continuous way. So the example like the mountain's elevations, like the rainfalls in a certain areas, or the depths of the oceans, or the temperature of an area. So they all like, you can't really find like a clear boundary, like where the number will change from one to another. So it's like always gradual change. So usually the model is like a function. They're functions that will map the spatial locations to the values. And another is the object-based, which is the one that it's the focus of this course, or it's called entity-based. So this one, basically, we try to model the boundary of spatial features, like the census block. And usually within the boundary, it represents a certain type of things, and they share a lot of properties, like a census block. They have the names, they have the population, and lots of other things, and they're shared by the whole census block. And it's good for expressing like discrete spatial entities. So we can have a boundary, and within the boundary, they have some common properties. Okay, so let's see example of using field and object models to see the forest stem. So this is an example where we can use both. So it's basically like we have a forest, and then in certain area of the forest, we have different plants, and we want to model this, like in which part we plant pine trees, and which part we have fir, and which part we have oak. And because here it's nicely separated, so each area is like a rectangle, and they're always in the nice boundary. So we can use both object or use the field views. So in the object views, we have like 3 polygons, right? And defining the boundaries, and each boundary we have a certain tree types. So it's like here, this tree, the tree species is pine, and we use the corners coordinate to define the boundaries, and that's fir, that's oak. So that seems pretty clear and easy to understand. And another way is called the field view. So the field view is like a function, and the function has, because it's in a 2-dimensional space, so we have x and y values. So the function takes x and y values. So for each pair of x, y values, and we can work out the function's value is basically the tree types. And it's a step function because we only have 3 values, right? Either pine or fir or oak. And so it's like within this range, x range and y range, and the function's value is pine. And within this x range and y range, the function value is fir. And within this is oak. So you can see that, okay, because we can use, so if this becomes like not a rectangle, but it's more like a curved shape or other shape, so we can always change the functions to reflect the values. And of course, then we have to change the boundaries as well. Yeah, that's like, Okay, so we're focusing more on the object view, and so we try to define like the boundaries as like shapes, and then usually we need a way to categorize different type of shapes, like geometries. So it's like we have the very basic ones like the point, and then we can have a single point or multiple point, and then we have like curve, and then so like just representing a line, whether it could be a straight line or it could be a curved line, so we call it a curve. And then we can have, underneath this, we can have like something called line string, again, representing like a, more like a straight line. And then we can have line and a linear ring, which represent like multiple lines. And then we can have a surface. So this is more like two-dimensional thing. And then for the surface, we have different shapes. Like we might have polygons, and then we have multiple polygons, and then we can have a collection of all of this, like multi-surface or multi-curve. Like so this is more like connected lines, and the multi-curve is like we might have multiple lines that they're not really connected, but they still, as a whole, they represent something. They have business meanings. Or multi-point, again. The point, they might not really join together, but they might represent something, like maybe all the branches of a certain bank. So that's like a basic model, basic way to organize like or categorize different shapes, spatial shapes. So example like point, usually it's by we define a point by giving coordinates, and if it's in a 2D space, and then the coordinate has like 2 values. If it's in 3D, there will be 3 values. And then we can have a collection of several points, or we have the line string. The simplest form is the piecewise like linear, given by the point, and usually we indicate like there's straight line between the point, like those ones. So it's like, so there's a line from, so they like indicate 3 points, and then 2 segments of lines connecting these 3 points. That's what we call line strings. And then the polygon is basically like 2D region whose boundary is given by all this corner point. And then a pair of points will define like a line, becomes the boundaries. And then we have a collection of polygons. And all of this usually in most of the spatial systems will implement those basic shapes. Okay, so the most basic thing, remember, we need to have is a point which is given by the coordinate, and the coordinate are usually like 2 or 3 or multiple values depending on the dimension of the space. So what's the meaning of the value? That's defined by something called coordinate systems. Like the unit of the values and where is the initial point. So that's what we call the coordinate systems. So you might have the point with the same value, but if they put in a different coordinate systems, they probably represent different things. And then the distance between the pair of points will mean very different things if they put in a different systems, and the way to calculate them will be quite different. So the coordinate system is basically a way to associate number with those points. And in particular, so the simplest one is what we call the two-dimensional like Cartesian coordinate, where there is like a point as the origin, and then we choose direction for the x-axis and the scale, and also then we have the y-axis, and then we have scale, which basically means what like number 1, like from 10 to 00 means, it means 1 centimeter or 1 meter or 1 kilometer. And this is like a flat space. And then there is a way to calculate the distance between two points. You can use the Euclidean distance. Okay, so that's for this is the very simple way. But usually for geospatial system, it's not really on a flat space, even though when the range is in a small area, it looks like flat, but it's not like flat. It's like a round space. So all this geospatial system, you have to. It's not really using the 2D Cartesian coordinate. It's two-dimensional, but it's not flat. It's curved, and also it doesn't really have this origin point called 0, 0, because it curves back. So the way to calculate distance is quite different, and there needs lots of special treatment when it's like curves back. So the Cartesian system and the Euclidean distance works reasonable in very small region when it's like approximately flat. But in bigger, if you want to calculate distance between two cities, and if they're far away, and then using the Cartesian, using like Euclidean distance, you will get it wrong. So yeah, the traditional one is we use the 2D with longitude and latitude, but we can also have 3D by adding the elevation there, if the elevation is also very important. And yeah, there are lots of things we need lots of places that need special treatment, like the surface is a sphere, so and then it's kind of like curves back. So this minus 179.10 and 179.10 looks pretty different on the surface, but they're actually pretty close. And then the line string might cross like the 180-degree longitude line, and then in that sense, in that way, when you calculate the distance, you might have to calculate like in two sides and then add them together. Or if a region includes the North Pole with latitude equals 90, and then to calculate the area of the region, and lots of other things need special handlings. So all of this can become pretty complicated, and it's hard to like for individual like developers to work everything out. So it's better to use a system. And even if you're really careful, it needs to consider that the Earth is not really perfectly round. But most of the time, we don't need to worry too much about that. Okay, so it's something people tend to ignore. In particular, it's very easy to ignore. In particular, when you look at the map, it looks like flat. So we can't. If we try to calculate, okay, if there's like figure out the bomb threat, and we know the radius, and then basically the easiest thing is like to calculate using this as the starting point, and then draw a circle, and then that would become the range of like a missile. But that's just an illusion, because first, even though we put everything in, like the map looks like flat, but we basically stretch lots of things. And most map, remember, there's always like a bias when people making map. They make Africa really tiny compared with Russia, but in fact, Africa is much bigger than Russia, even though in the map it usually looks smaller. So there's lots of distortion and stretch. So it's not really flat. And so initially, like even the very like economics magazine, which is considered as a pretty serious magazine, made this mistake when they calculate the missile threat. They just like draw a circle here, which is definitely not right. So they have to, when you consider the round fact, and then it's much larger actually. You will work out something much larger here. When you take into the consideration the world is not flat, it's round. Yeah, that's just another way. How you calculate a missile's range. Okay, so that's the data model. So usually we're focusing more on the object-based model, and then we have basic types like point, and usually we use coordinate to represent the point, and then starting from point, we can assemble more complicated spatial object, and then putting them on a coordinate system. So we already seen one simple example of how we can calculate a spatial operation by starting from a point, calculating how far away like a missile can reach. So that's one type of operations. It's more like the metric type of operations, and that's a very simple type of operations. And there are a lot of other operations processing we can do on spatial object. One is called like set-based. So it's like a set operation because most of the spatial object represent some area or something. So we can use set operation to do some calculation, like calculate the intersect of two polygons, or calculate the union of two polygons. They usually provide, like, the intersect will produce like another polygon. So that's some typical operation. And then there's also topological operation. So if we want to see like whether or not the boundary of USA like touch the boundary of Canada, so that's like a topological operation, like how the two shapes, like whether they touch or they overlap or they disjoint. So there's a few topological operations. And then there's directional, like east, northwest, or others. And then the metric is more like calculating the distance. So some of the operations are relatively easy to represent and to calculate, because we can use regular math to do it, like the set operation and others. Set operation and metric operation can easily use like normal math to do it, but not really topological. This is something like very unique to the spatial object. So what's some special features of this? So first is like it's invariant under elastic deformation. Like if we don't tear, but if we stretch it or we compress it, and then the relationship doesn't really change. It's just like when we put like a round globe in a flat map, and then all the countries' relative topological relationship it's still the same. So if two countries touch boundaries on the globe, and then when we put it on a map, they should be like the boundary should touch as well. So the example queries could be like, what is the topological operations? Or if we have a topological operation, we want to find all the object that has shows this like features, like find all the object that touch with each other, or find all the object that within one object. So an issue is we can express it in text easily. Like we want to see, like we can use touch, we can use disjoint, we can use contains, or overlaps, or a few other texts. So we can describe this textually very well, but this doesn't really help us to actually calculate it. So we want to be able to express this mathematically. Then this can help us to calculate this more efficiently. Not like the others, like for set, we can just reuse the set operation. And then for the matrix one, we can use other math operation. But this is a bit hard. So, because it's kind of related with like the boundaries and interiors and others, so the researchers come up with some concept, like for each shape or object, it always has like an interior, it has a boundary, and because the shape is always in some world, like in a coordinate system, so there is also exterior, and assuming the world has a bound, and then there's always the exterior, so it's like a limited world. So for instance, if this is an object, and the green is this object's interior, and the red one is its boundary. Right? And then suppose this is the universe, like in U, and then the blue part is like the exterior. So every object has these three things: has a boundary, has interior, has exterior. If it's put in a universe with like a limited universe, and we can use some math term to represent this. So it's like A0, and then this is the boundary of A, and this A bar is like the exterior of A. Now, if we have a pair of objects, and then both have this, and if we know the relationship between all of this, like A's interior, how is A's interior like interact with B's interior, and how is A's boundary interact with B's boundary, or A's exterior with B's exterior, then we are able to work out the topological relationship between this pair of objects. Yeah, so many of this basically can be specified using their intersection. So the 9 intersection model is, so this is like a relationship between a pair of objects, and each object has three features: interior, exterior, and boundary. So in total, there are like 9 pairs of intersections. Like you have intersection between the interiors, boundaries, and exteriors of A and B. So in total, there are 9 of them, and this is what we call 9 intersection model. So if we know all the values of this, and we can work out what is the topological relationship between A and B. So here we assume it's in a 2D space. In the 3D one, it will be quite different. So this can be arranged in a 3x3 matrix, and assuming like this one, so the row represent A, and the first row represent A's interior, and the second row represent A's boundary, and the last row represent A's exterior, and the column represent B, and then this is B's interior, B's boundary, and B's exterior, and then these are all the possible intersections. So not all values are valid, right? There is certain values that you can't really, it's not possible. But so these are all the possible values. So we can specify topological operation basically using the models. And then 0 means there's no intersection, 1 means there's intersection. So here, this is what we call disjoint. So A and B are totally independent to each other. So disjoint means basically A's exterior, which is all of this, will intersect with B's everything. So because A's exterior, remember, intersect with the boundary, the interior, and B's exterior. And also vice versa. So B's exterior also intersect with A's everything. So that means that's disjoint. So this is A. A's exterior is here, and B's exterior is here. So if A's exterior intersect with B's everything, so we put all 1 here, and we put all 1 here, and all of these are 0. They are not intersecting. So that's like this. That's A's exterior intersect with B's interior, boundary, and exterior, and also B's ones the same thing. So that means disjoint, and the others are not really intersect. So this is another one called A contains B. So B is basically totally inside A. So which means A's interior, that's intersect with B's everything, right? And then B's exterior is all the outside. also intersect with A's everything. So this is A's interior, intersect with B's everything, so it's all ones here. And this is B's exterior, intersect with A's everything, so it's all ones here. So that means contains. And then for the others, you can work out yourself. So that's all the valid combination. And that's like a mathematical way to represent those topological operations. Okay, so that's the data model, and then the all different sort of operations we can have on spatial data. Now let's see if we store data in a database, what sort of queries we can run. Okay, so one type is called spatial processing, and this one doesn't really involve queries. It's more like processing. So what it means is, okay, so we want to find one or more entities, things in the database, but when we do the query, it's based on non-spatial aspect. And once we get the data out, we get the result, we want to run some spatial operations to work out the spatial information. So this is called spatial processing, because the spatial operation is not really involved in the query. It's involved in the afterwards processing. So for instance, if we want to find the length of the river called Mississippi, so the query is based on the name, which is a non-spatial property. And then if we're not really storing like a numerical value as the length in the database, we need to work it out. So then after we find this river and we find the spatial representation of the river, we have to use some spatial operation to work out the length. So that's called spatial processing. Or find the total area of all countries whose population exceeds 1 million. And then again, the query is based on non-spatial property. And once we find the result rows, and then we need to run spatial queries to work out the area. Again, we're assuming the area is not really stored. We need to work out and then sum it up. So this is called processing. So this doesn't really need a lot of extra work. We use conventional index or table, like full table scan, to get the rows we want, and then we use spatial functions to work out the final result. So that's called spatial processing. So spatial query is like, okay, the actual query does involve spatial data and spatial operations. Like find the spatial attribute, find items whose spatial attribute has certain properties, like find rivers whose length is at least 10,000 something kilometers. So again, assuming the length is not stored as like a static number, we have to work it out. And then, so this is like a spatial query. So the where clause will involve spatial operations. The typical process is, if we don't have index, we have to scan all the rows, apply appropriate spatial operations to the spatial attributes of each. But it might be helped with index. So let's see what's different type of queries we might have. So the special kind is called spatial range query. So usually we differentiate query between like point query and range query. Point query is like you just want to find like a single data point, and range query is like you want to find a collection of data. So in a spatial query, there's also this thing. We can have spatial range queries. So basically this but it's slightly different definition to the regular range queries. So it involves like conditions. So the query condition involves a topological or metric relationship of a given object, like find all bookshops whose location is inside a given region. So the region it's like a range, and we want to find all the bookshop within it, or find all the farms that contain part of like a given curve, which is like maybe the curve represents like a river or something, or find all the rivers that flows through a given region, or find all bookshops within 100 kilometers of a given point. So all of this involves some kind of area. That's called spatial range queries. So the simple processing is we scan the appropriate table, like apply appropriate spatial operations to each item's spatial attribute. Again, that will be very inefficient if the table is pretty big. So usually we need 2 steps. Most of the spatial queries operate in 2 steps. The first step is we run a filter step to find a small set where the condition might be feasible, and then we can optimize different. We can use index to find a small set, and usually finding small set doesn't involve very complicated spatial operation, and then we refine the result by checking that it actually satisfies the condition. So this is a typical way, like if we want to find objects that intersect a query region, and usually the first step, like the filtering step, is so the spatial object, you can have all different kind of shapes, but most systems will try to use a very simple shape, like a rectangle, to represent it. And because rectangle is much easier to handle than an irregular kind of shape. So if we associate each object with a simple shape like a rectangle, and the rectangle basically bound it. So that's minimal, that we call the minimal bounding rectangle. It's like if this is a triangle, so this is a minimal bounding rectangle. And if this is this irregular shape, that's the minimal bounding rectangle. So we always put them in the smallest rectangle that will cover all of it. And once we get the rectangle, and then the filter step is basically to check, like if the object MBR doesn't really intersect the query one, and then there's no possibility that the object itself will intersect with the query. So we can use this to filter out a large set of objects that is not possible. So we get a smaller subset. So if this is the query region, and these are all the data object. So, and then first step is we try to see if the query's region will intersect with the MBR of all the object. And then this one is not really intersect. And then, so we don't need to further consider that. But all of this intersect with it, so they are candidate object. So by doing this, we can get rid of some things. And this checking if 2 rectangles intersect with each other, it's pretty simple. And then we do a refine step by, now we have to work out the actual, using the actual object. And the refine step will give you the final result. And usually this can be assisted with index and can be done pretty efficiently. And this is the one that's more costive. Okay, so that's spatial range query, and usually processed using 2 steps. And then we have this nearest neighbor query. Again, that's something probably you don't really find a counterpart in the regular query, normal like data type based query. So like find entities that are as close as possible to a given location, or you might sort them and you find the top K nearest like neighbors. 5 close restaurants to this location and return them ranked by closeness. So the simple processing again is we scan all of them, compute the distance, and then keep track of the ones with lowest distance seen so far. And again, that's not very efficient, so we want to use index-based algorithm, which is the next week. We're going to cover next week. Okay, join query. So join query in any context is very, very complicated. And usually, if possible, we try to avoid it. But you have to provide, as a system design or implement, as a system, you still need to provide such functionalities, but you always kind of warn the users, try not to use it. So we do have spatial joins as well. So join involves single table variables, can be done in a single scan, but sometimes we have joins that involve a combination of objects. Like if we want to find a pair of town or country where the town lies within the country, again, assuming we don't have pre-knowledge which town belong to which country, we need to work it out by their actual physical location. So that's if town and country are stored in different like tables, or a pair of rivers that pass within 5 km of one another. So that all of this needs to, it's like a join, right? Even if in the same table, you have to do a self-join to create the pairs, and then you have to work out. It's like to create the pairs, and then you kind of work out if the pairs satisfy the conditions. So it's similar to non-spatial join. They're usually pretty expensive to process, and sometimes instead of using the non-spatial join way and to produce like all possible pairs, we might be able to have some optimized ways of doing it. So this is an example. For certain spatial queries, spatial join, we might have a bit more efficient way instead of producing like all possible pairs and then examine them one by one. So that's an example of how we can carry out spatial join in a slightly more efficient way. So if we have two relations of rectangles, R and S, and we want to determine the pair of intersecting rectangles. So we don't care if R intersect with it, any R intersect with itself, but we want to find out like the intersecting R and S. So like R4, S2, or S2, R1, or R1, S3, they are like intersecting pairs we are interested in. So this is a typical join type of query. So instead of producing all the possible like pairs and check them, we can design a special customized way to process this. First, we can sort. So assuming because they're all rectangles, so they're all kind of, we don't need to, because it's rectangles, so we don't need to remember all 4 corners. Just the bottom left and the top right would be enough. So we use the bottom left and top right to represent like a rectangle. And we don't need to do this because then we can work out those ones. And then we can sort all the rectangles in both based on the bottom left x-axis. And it becomes something like, so we only look at one dimension. So it becomes something like this. And now we have R4, S2, S1, R1 like this. And then once we have this, we can traverse this list and just in one go, and then to produce the result. So the complexity is like n plus m, right? Instead of like n times m. So how do we do it? Basically, starting from the first rectangle T, and then we go through this, and we don't really look at R's because we're not interested. So we look at all this S, and until we find a particular SF whose left x is greater than the right x of this one. So we know the right x by looking at the top right corner. So first we find S2, and this is not greater than, it's still within. So this is the right x of the first rectangle. And this one is not greater than that, so we move on. We go to S1. And S1's left is greater than this, so it's like, okay, we stop here. And everything we've seen so far is basically, it's possible to intersect on the X range. All right. So it's possible to intersect on the X-axis, but we need to check if it also intersects on the Y. So we need to check if they intersect in the Y-axis. And then if it is, then that's a result. And this one it is. And now we move to the next rectangle, and so yeah, that's the one. Then next, we kind of move here and then repeat the same thing until we find everything. So that's basically how that's a very specially designed way to answer spatial join queries. Its complexity is less than the regular join ones. Okay, I think that's all for the lecture. So if you are in Tuesday labs, you can move to the labs and then start preparing for your demo. And the Wednesday ones, we'll go to the Wednesday demos.
Material from which week will be covered in that quiz?
It should be up to, starting from where quiz 1 is not covered.
Sorry?
Starting from where quiz 1 is not covered.
Okay. So
and to week 11.
To week 11. Okay.
I'll announce that.
Okay.
Yeah, in week 11.
Sorry?
It won't be. So to give you a taste of what you will see in the in the final exam, so this time will be all short answer questions.
Okay.
Yeah.
That's
what you will see in the final exam. You have some multiple choices and the short answer questions.
Are we going to write cards? Or is that...